Hello everyone. For my literature review, I chose graphene interconnects. So I'll be going over why we're searching for new materials for interconnects, what graphene is, its atomic structure, mechanical and electrical properties, the structure provides that allows it to have higher performance than copper, one of the potential impedance models for theoretical modeling of graphene, propagation delays based on the model, and impedance of graphene at high frequencies, just because conductors behave a little differently with high frequency AC current compared to DC, and it's even more different with graphene. And then finally, I'll go over large scale manufacturing challenges that we're currently facing with graphene. So why are we searching for new materials? As transistors are getting smaller, computer chips are getting more and more dense, so even with increased power efficiency, there's a lot of heat that needs to be dissipated quickly. Currently we use copper, which works well, but we're approaching its physical limits in terms of resistivity and thermal conductivity. Copper also suffers from electromigration, and that's where the copper atoms themselves move with the electrons when a voltage is applied. So if you want to continue to scale and pack transistors more densely and increase power efficiency, we need to find a new material that has higher performance than copper. So what is graphene? Graphene is being explored as a potential new material for interconnects. Graphene is a one atom thick honeycomb structure consisting of sp2 hybridized carbon atoms. sp2 has to do with electron orbitals and how electrons are shared between atoms. So if you look at figure 2a, on the top in light blue, the flat structure, that's graphene. So in that structure, a carbon atom is bonded to 3 other carbon atoms. Graphene is the building block of both carbon nanotubes and graphite. Carbon nanotubes are one layer of graphene rolled into a cylinder, which is shown in the maroon color in figure 2a. Graphite is flat layers of graphene stacked on top of each other, and that's shown in figure 2a all the way to the right in dark blue. The dark green structure all the way to the left in figure 2a, that's quantum dots. I won't be talking about them in this presentation, but just for your information, I believe those are quantum dots. Just based on the research I've done. The source that I got this particular figure from didn't say that. Yeah, but just based on other research, I believe it's quantum dots, which is basically a dense ball of graphene. So one thing to note about graphite is the layers of graphene are at a slight angle to one another, and that's shown in figure 2b. So this detail will become more important when we distinguish between graphite and multi-layer graphene. So even though both are multiple layers of graphene stacked, the fact that graphene layers are at a slight angle in graphite gives it different mechanical and electrical properties compared to multi-layer graphene where they're not stacked at an angle. So graphene was isolated by Andrei Geim and Konstantin Novoselov in 2004. I think I'm pronouncing that correctly. So they isolated graphene from graphite in 2004 using the Scotch tape method. So that method is kind of like it sounds. They basically took a piece of Scotch tape and pasted it on graphite and ripped it off to get a thin layer of graphite. And they then proceeded to fold that piece of tape on itself and rip it off again to get an even thinner layer of graphite. And they repeated this about 10 to 20 times and eventually ended up with a very, very thin layer of graphite that's only a few atoms thick. So the other researchers then took this method and used it to successfully isolate a one atom thick layer of graphene from graphite. So it was a relatively simple method, but it was also an important advancement. In fact, it was so important that in 2010, Geim and Novoselov won the Nobel Prize in Physics for this method and for isolating graphene. So what is graphene's atomic structure? So there are 2 important things to note about it. It has 2 types of lattice structures. Armchair, where there's a dip or a climb between the 6 carbon rings, and that's shown in figure 3a, and the zigzag, where the dip doesn't exist, and that's shown in figure 3b. The zigzag structure is currently being researched as a potential replacement for copper interconnects because of its low resistivity and thermal conductivity compared to the armchair structure. So graphene interconnects are also referred to as nanoribbons, graphene nanoribbons. Nano because of the scale of the interconnects, and ribbons for width less than 15 nanometers. There are single layer graphene nanoribbons, which is a single layer of graphene, and multi-layer graphene nanoribbons, where multiple graphene layers less than 15 nanometers wide are stacked on top of each other, so either vertically or horizontally, or they're folded. So in the folded structure, it can be vertical or horizontal. So these structures are shown in figure 4. So HGNR is horizontal, vertical is VGNR, and folded is FGNR. In this particular figure, figure 4, the FGNR is horizontal. The folds in the FGNR are actually fractional carbon nanotubes. So if you remember from a couple of slides ago, I think, carbon nanotubes are one layer of graphene rolled into a cylinder or a tube. So in this case, the fold is a fractional carbon nanotube because it's a graphene layer folded into a semicircle. So it's essentially a fractional carbon nanotube. And so let's look at its electrical and mechanical properties. The atomic structure of graphene gives it amazing mechanical properties. It's 200 times stronger than steel. It has a Young's modulus of 1 terapascals. Young's modulus measures the stiffness of a material. Compared to some of the hardest materials that we're familiar with, like titanium and steel and diamond, it either beats them, or in the case of diamond, it's comparable. It has very high thermal conductivity, which allows for fast heat dissipation. Diamonds are used in some computers for cooling because it has high thermal conductivity, but it's also extremely expensive. So graphene could provide comparable cooling at a much lower cost. Copper, by comparison, has about 5 times lower thermal conductivity than graphene. The conductivity of graphene changes when it's bent or curved, so this is a mechanical or electrical property. Mechanical / electrical, so there's a bit of both involved. So for example, with carbon nanotubes, if it's bent or if it's rolled one way, it acts like a metal. And if it's rolled a different way, it acts like a semiconductor. So a similar story with graphene. When it's bent, the conductivity changes. So an additional application for graphene, in addition to being interconnects, is being a pressure sensor. So in terms of electrical properties, the first thing we need to discuss is why graphene is highly conductive. So if you remember from 2 slides ago, each carbon atom is bonded to 3 other carbon atoms in graphene. So each carbon atom, shares 3 of its electrons. So a carbon has 4 electrons in its outer shell. So what happens to the 1 electron that's not being shared? Well, it's free to move around. So just like in copper or iron or other conductive metals, what makes them conductive is the ability of loosely connected electrons to flow easily. So that's also the case for graphene. So charge carriers move as if they have 0 effective mass. The carrier mobility seems to vary quite a bit according to the research papers I read. So some put it in the 2,000 to 5,000 centimeter squared per volt second range, others put it in the 4,000 to 8,000 range. But one thing all the papers seem to agree on is that the mobility changes with width. So it's possible that the different ranges are due to different widths. The conductivity of graphene changes as it's bent or curved, as I mentioned in the last slide, but it also changes based on width, and we'll see how in later slides and to what extent. The single layer graphene has 0 band gap energy. Band gap energy is the energy gap between the top of the valence band and the bottom of the conduction band. So essentially it's energy required to allow electrons to flow. So 0 band gap energy means that it requires little to no energy to get electrons to flow. Multilayer graphene does have band gap energy, which is adjustable based on width, and the equation is shown here. So the range is 0 to 0.25 eV, and the equation is alpha over WGNR plus W naught. That gives you the band gap energy. So let's look at impedance modeling. In order to use graphene, we need to be able to model it. Single layer versus multi-layer have different conductivities, which I mentioned in the electrical properties slide. Single layer graphene doesn't have band gap, but multi-layer does, although it's very small. The gap in multi-layer can be made even smaller with doping. Multi-layer graphene nanoribbons can be modeled as several single-layer graphene stacked on top of each other, and this is precisely what 2 researchers did with their equivalent single conductor model. So we'll look at that next. But here's the geometries of SLGNR and MLGNR. SLGNR is single-layer graphene nanoribbon, MLGNR multi-layer graphene nanoribbon. Okay, so figure 6 shows the model. The interconnect is the ESC model. The interconnect is being driven by an inverter and the load, and it has a load CL. All the impedance characteristics are per unit length, except RC. RC is the quantum resistance. Quantum resistance has to do with the quantum Hall effect, which is quantized for graphene. Yeah, that's beyond the scope of this presentation. I didn't fully understand it, but that's what RC is. Similar story with quantum capacitance. It's due to the quantum Hall effect, but again, I didn't fully understand it. So we're all familiar with regular resistance, magnetic inductance, and electrostatic capacitance. So those are the impedance characteristics that we've been working with both this quarter and the previous quarter. I'm not sure if we took kinetic inductance into account, when we worked with the models in class, but the researchers did for the ESC model. Kinetic inductance is the inductance caused by the kinetic energy of a moving electron. So at the nanoscale, the effect of that matters as well. So researchers did take it into account. So let's start with resistance for single layer graphene. The mean free path is the path an electron takes, and it's given by the lambda n equation. Scattering is when the electron deviates from the mean free path, and it ranges between 0 and 1. The resistance equation for a single graphene sheet is given by the RSLGNR equation, and for multilayer graphene, the resistance is simply the RSLGNR number divided by the number of layers. So for example, let's say the RSLGNR number is 20 ohms, and you have 4 layers, so 20 divided by 4, 5 ohms. That would be the equivalent resistance for an MLGNR made up of 4 graphene layers. So in the graphs below, in figure 7, you can see the resistance for various MLGNR structures at different Fermi levels, and this is assuming there's no scattering. So in figure A, it looks like HGNR has lower resistance for 7 nanometers or less, and we are approaching that in terms of conventional lithography, but scientists prefer FGNR due to the higher band gap and the other impedance characteristics. So we'll see that in the next slides, how FGNR performs compared to HGNR. But FGNR is the preferred MLGNR structure. Okay, so for temperature coefficient of resistance, resistance changes as temperature increases or decreases, but for some materials, so does the temperature coefficient. And so with copper and GNR, the coefficient stays constant with length, but decreases as the width decreases. So you can see that with copper, when the width decreases, so does the coefficient. But with carbon nanotubes, the coefficient increases as length increases and the width decreases. So multi-walled carbon nanotubes, shown as NW in the graph, have lower coefficients than single-walled carbon nanotubes, and that's shown as SW in the graph. So table 1 shows the physical dimensions, resistivity, reference temperature coefficient, for producing the graph. And so these are the equations for the various inductances. Figure 8 shows that the number of layers increases, the overall inductance decreases. Inductance also decreases with width according to the equations that are shown there for coupling and magnetic inductance. So the plots at the bottom in figure 9, and these are relatively high frequencies, but the thing to take away is that FGNR outperforms copper, as well as the other MLGNR structures at Fermi levels 0.2 and above, MLGNR meaning multi-layer graphene nanoribbons. So this is one area where FGNR excels and why scientists prefer it over HGNR. So even though HGNR performs well at a 0.1 Fermi level and 7 nanometers or less, in terms of inductance, FGNR outperforms. So for capacitance, the various capacitance equations are shown here. It's a little difficult to read in figure 10, but it shows that for a given width, in this case 15 nanometers, that's what the title says, equivalent capacitance increases as the number of layers increase, but there's a maximum after which capacitance plateaus. I couldn't find a plot for width versus capacitance, but capacitance tends to increase with width, at least according to the coupling and electrostatic capacitance equations. But I also assume that it plateaus at some point. The triangle, squares, and diamond symbols in figure 10, those are the equivalent capacitances using a more precise quantum capacitance equation. So what the authors were trying to do is make a comparison between the more precise equation and the approximate quantum capacitance equation that's listed here. And they were trying to show that excuse me, that you basically get very similar results. You can use some approximate quantum capacitance equation without a lot of loss in precision, and it has a lower computational cost. The approximate equation does. The approximate one are the solid lines. Alright, so let's look at propagation delay. So how does width and number of channels affect it? So the top left graph confirms that for a given width, delay decreases by a factor of n, where n is the number of layers. The top right and bottom graph show that having a large number of layers can compensate for increases in length, which makes it ideal for global interconnects. So for example, comparing n equals 2 and n equals 20 for 15 nanometer width, increasing length by 4 times increases delay by 2, but for n equals 20, increasing the length by 4 times, only increases delay. Hang on, I think I messed that up. If you compare n equals 2 and n equals 20 for 15 nanometers, increasing length by 4 increases delay by 2 times for n equals 20, but 4 times for n equals 2. So having more layers definitely helps. But one thing to note here though is that there was a 10 times increase in the number of wires, but it only resulted in halving the propagation delay. So there is an upper limit to how many layers you can add before getting diminishing returns. So that's one thing to keep in mind, but yeah, definitely adding more layers decreases propagation delay. So MLGNR interconnect propagation delay. So the propagation delay for the different MLGNR structures are shown here for different Fermi levels, and at p equals 1.0, so that equals full scattering. I don't think I ever explained Fermi levels. So Fermi levels are the energy levels for different electrons. So that's also beyond the scope of this presentation, but yeah, it has to do with energy levels of electrons. So you can see that FGNR outperforms copper and the other MLGNR structures as well. So in terms of delay, so this is also another reason scientists prefer FGNR over VGNR or HGNR. Alright, let's look at graphene for high frequency. So at higher frequencies, all conductors suffer from what's called a skin effect. So this is a consequence of physics where the current doesn't use the full area of the conductor to propagate through, and that's shown in figure 13. So you can see the dark blue, that's where very low current density, and the dark red is high current density. So with the normal skin effect, NSE, for both p equals 0 and p equals 1, you can see that the outermost layer is very dark red, and it ends up getting used. But for graphene, it suffers from what's called ASE, so anomalous skin effect. And for both p equals 0 and p equals 1, you can see that it doesn't even use the full outer surface area. It uses the top. For p equals 1, it uses the very top of the conductor as well as the very bottom of the conductor. The sides, are not even being used that much. Sides, and the sides of the conductor on the surface. Yeah, so it's definitely better to have full scattering in terms of skin effect. But yeah, because of ASE, the resistance and inductance tends to be larger compared to if graphene had suffered from NSE. So we'll see that in later slides, but yeah, the idea is graphene suffers from ASE, and that's kind of the takeaway here. Yeah, so here we have a comparison side by side of NSE and ASE. So for resistance, you can see that because of ASE, at p equals 1, the resistance is higher than compared to NSE, and the inductance is also higher. Yeah, it's definitely better to have full scattering at higher frequencies, because of the ASE effect. So that's odd compared to if you had NSE and full scattering, it would be it would be worse. So graphene is unique in that case. Yeah, so this just compares the two, and it shows you the uniqueness of graphene. But the thing to take away though is that even with ASE, graphene is still a better conductor compared to copper. Yeah, despite what's being shown here, it's a better conductor than copper. So current manufacturing challenges. We need large sheets of graphene to use used with conventional lithography. So currently the primary manufacturing method is graphite exfoliation, so either physical or chemical. The Scotch tape method can be kind of seen as a physical exfoliation method. So it's mostly used in academia, the exfoliation method is. For research, it isn't quite feasible for large-scale manufacturing. For large-scale manufacturing, they're looking at the chemical vapor deposition method. So that's where graphene is grown on metal, like copper or nickel, by combining gas that has carbon in it with a high-temperature reaction chamber. The only downside is it requires a lot of energy. It creates harsh chemical byproducts. And once the graphene is grown on either copper or nickel, it has to be transferred. And during transfer, it's very susceptible to damage. It's only one atom thick. And if it is damaged, so it's either bent or there's holes in it or it gets wrinkled, that changes the conductivity. So remember that from the electrical properties slide. Any changes in its physical shape can affect the conductivity. So it could end up getting lower performance than copper. So that's one of the downsides with chemical vapor deposition. But that's currently I think the best method we currently have. I think other methods are being explored. Other alternatives are being explored to CVD. But this is kind of what we have right now. So conclusions: graphene 5 times more thermally conductive than copper, 10 times more electrically conductive, and the electrical conductivity can be adjusted based on shape or width. The ESC model is one of the potential models for modeling graphene. HGNR has the lowest R, although that gets comparable to FGNR at 0.4 Fermi level. FGNR has better propagation delay, as well as inductance and capacitance. And the zigzag structure is preferred over the armchair structure for FGNR, HGNR, VGNR, basically all the MLGNR structures, as well as single layer graphene structure. So graphene suffers from the anomalous skin effect at high frequency rather than the normal skin effect, so that results in higher resistance and inductance compared to a normal skin effect. But it's still a better conductor than copper is, even with that effect taken into account. So the current manufacturing challenges: graphite exfoliation, it's not feasible for large scale, it's only being used in academia. Chemical vapor deposition, or CVD, is too power hungry, creates harsh chemical byproducts, and during transfer of graphene from the substrate to wherever you want to place it in, it's susceptible to physical damage, which can lower its properties in terms of conductivity. Alright, so these are my references. Yeah, so that's it. I'm not sure if we're supposed to present questions, but if we are, I look forward to them. Thank you.